concept of his office being out in the fields, out in the pastures, out in Florida. Very, very important. So Jack's going to give us a welcome, talk a little bit about IFAS and the University of Florida, and let me turn this over to you. Good to have you.
Thank you very much, Ernie. Good morning, everyone. Well, welcome to Gainesville and Big Data and Decision Making, the Future of Water Space. It's a heck of a title. My thanks to Stan Bronson for choosing the University of Florida as the location for this very important conference. With so many accomplished scientists present here today to discuss something as important as the future of water, I want the chance to make the case why you should be plugging Gainesville into your GPSs for future reference. And hopefully we'll be participating with partnering with our faculty on the many water issues we face in the state of Florida. There are a lot of reasons to come back to UF. Many of you are familiar with them, but I want to mention just a few. And I'll get to the programmatic reasons in a moment. First, though, you need to know that a great reason to connect to UF and with IFAS right now is timing. This is a special moment for us, and now's your chance to get on board with work that has so much potential to change the world. Just last Friday, we swore in the 12th president of the University of Florida, a guy who really gets the land-grant mission. What that means in this room is that I don't have to remind him of the value of natural resources research, although I often do anyway. And last week, I went to the dedication of what we call HyperGator 2. UF is now home to the most powerful supercomputer in the state, the most powerful university supercomputer in the southeast of the United States, and the third fastest university supercomputer in the country. I think that speaks for itself in terms of our capacity. But to put it in perspective, our supercomputer can hold 21 million times more data than the computer program on Apollo 11 that put man on the moon. You'll need HyperGator itself to count the potential applications for this kind of computing power. One example I came across last week is from one of our doctoral candidates named Caroline Storr, who's in our School of Forest Resources and Conservation. She's using the supercomputer for DNA sequencing to determine where erosion beetles are coming from and how they spread. You may know that they carry wilt virus, which is a great threat to the avocado industry. But to foresters also are curious who want to know if the beetle hitchhikes on harvested wood. And just last year, when the state legislature designated us as a preeminent university, it gave us the funding to hire more than 100 preeminent scientists from around the country and from around the world. It's a university-wide initiative that's designed to raise our national profile so that we can make even a greater impact on the major issues we all face. With so many hires authorized and funded at once, we had a unique opportunity and we took a unique approach. We did not scatter the positions out like gold coins in various departments. Instead, we identified the big issues of the day where we could really make our mark. Then we began searching for top-notch people to join interdisciplinary teams to research those issues from multiple angles. IFAS has a hand in many of these preeminent areas, including biodiversity, bioinformatics, food systems, plant genetics, and more. You might notice the thread running through these seemingly disparate subjects. Expertise in water has to be part of the equation. And last summer, IFAS also got state funding for an additional 40 new faculty positions, who again will be joining multidisciplinary research teams devoted to topics such as sea level rise, sustainable fisheries, healthy forests, and smart land use, to name a few. We're also bringing on 3 multi-county extension agents who will be dedicated to water conservation and water quality protection, working with 3 of our 5 water management districts. We hope to get 2 more of those water agents funded by the legislature this coming session. So we're getting a huge infusion of new intellectual energy to join our already accomplished faculty. We're trying to build academic homes as fast as our new neighbors are moving in. Just this year, we launched the Institute for Sustainable Food Systems, the Nature Coast Biological Station, in the Plant Innovation Center. So you can see there's a lot of momentum that has been generated here just the past 24 months. It's an exciting time to be at the University of Florida or to be affiliated with us. We're not only resourceful, but relevant. Our Water Institute is a go-to source for policymakers trying to reconcile competing water interests. The Florida Climate Institute is serving the entire world with its climate scenarios and options for how to respond. We've had a soil and water science department for more than 100 years. I could go on and on. The point is our status as a comprehensive public land-grant university makes us a big tent under which all of you can fit and find partners that will help take your work to another level and have you help us to take our work to another level. We have an incredible sense of mission here. We want to change the world, alleviate suffering, and keep this planet habitable for hundreds of years in the future. We promote agriculture and natural resources with a focus on how we can address perhaps the grandest challenge of our time, feeding 7.5 billion people by 2050. Of course, at the same time, we need to protect the ecosystem services like water that make agriculture possible, deliver that food in a safe and secure way, and a worldwide efficient distribution system under an umbrella of dramatic climate change. When I say food, I also include fiber and energy for clothing, shelter, and warmth. Now, as everyone here knows, it's not just an agricultural problem, it's a natural resources problem, it's a human health issue, an engineering problem, and a social, political, and economic one as well. It is the scientists at land-grant universities who have the expertise in addressing these issues. It is in land-grant universities where people are trained in agriculture, wildlife, food safety, food security, fisheries, engineering, ecology, and human health. Florida's premier land-grant university can provide so much of the infrastructure necessary to mount our best efforts as a scientific community to address this grand challenge of our time. There are other reasons for you to come back besides our programs and institutes, namely our people. Several of the UF people you'd be most interested in are here today at our conference. People like Tom Fraser, the director of our School for Natural Resources and the Environment. Loretta Hammond, chairwoman of the IFAS Department of Agriculture and Biological Engineering, who last year was named a fellow of the American Society of Agriculture and Biological Engineers. Rafael Munoz-Carpena, a professor in Dr. Hammond's department, and a 2013 Water Institute faculty fellow, and a member of the Spanish National Academy of Sciences. Kirk Hatfield, director of the Engineering School of Sustainable Infrastructure and the Environment, an IFAS guy like the others, but a distinguished academic nonetheless. So if you have a chance to visit with these folks and others while you're here, I'm sure that they will want to visit with you and get to know you better. I've seen the roster of attendees, so I don't need to make your case as distinguished scholars and leaders. The University of Florida and IFAS could be happier that you'll be our guest for the next 2 days. To me, it doesn't really matter what this event is called. The title stand shows it's pretty broad, it can mean a lot of things. I'm just glad it's here. The reason I want to talk to you is that so many top minds in the same ballroom, there's much potential for good things to come out of it. So please, start planning your return trip now. Figure out where your gateway to the university is, and Tom Fraser business card. On Friday, you can start registering for the Water Institute's 5th annual symposium on February 16th and 17th. So thank you, Stan, for partnering with the university and IFAS to get all these water and data experts on campus. It's going to be a great 2 days. Thanks to all of you who have come here today. Enjoy the conference. What I hope is just the latest in a series of business you'll make at the University of Florida. Thank you.
Thank you very much, Jack. And Jack was in 2013 one of our delegates to our Netherlands program, and I can tell you that he is very adept at dancing on top of tables. So I'm kidding, Jack. Before Will gets up, and what I'd like to say about this conference is that this is going to be very interactive. And there's going to be a question that everybody needs to think about during the entire day, and we're going to have a breakout session at the end of the day to kind of congeal what you've come up with. And that is, the question with big data is that data is, we're creating mountains of it. What do we do with it? And so I want to throw out to you the question of today, which will be different than the question of tomorrow. And that is, what do we need? What are the things that you see in from your perspective, not only from Hank and Gretchen at the federal level, but at the state level from the water management districts? What is it that that needs to happen in order to make big data useful? And so just put down ideas. There's paper and pen on the table. We'll have a breakout session, collect those, and kind of prioritize those. But as you hear the speakers today, that's the thing that we'd like you to focus on for having a product that we'll put out at the end of this conference. So, Ernie, I think Ernie's out of the room. So anyway, okay, if I could introduce you.
Yeah.
Will Sarni is from the firm of Deloitte. And when did the Deloitte and Touche, when did the Touche get dropped?
Well, it didn't get dropped. It's actually the global firm.
Oh, okay.
So it's,
Yeah.
don't be alarmed, it's still there.
Oh, it's still there. Okay. And I think you're number 2 or 3 in the world in size. So,
Number 1 in consulting, but Tom may know.
yeah.
Consulting is what we deal with, so our number 1.
Right, and the largest firm. So, Will's been for 5 years with Deloitte, and is also on the advisory board of a organization we work with very closely. We'll talk about later. That's doing the broadcast for the Water Network, and so he does a lot of global work. You can read his background right there. But Will, let's go ahead and get you going. It'll take just a second to.
So can everyone hear me without the mic? Not very well. Okay. I had high hopes. So first of all, thank you for the opportunity to be here. This is sort of the perfect keynote address. I have about 30 slides in 30 minutes, which means there's no time for Q&A. So for a consultant, that's perfect. And the second is that Stan has no idea what I'm going to say. So I'll surprise you, Stan. So I sit in Deloitte Consulting, which means I don't do tax or audit work. I lead our water strategy practice in the US, and I co-lead a global community practice. So what you'll see is that very little of the discussion over the next 30 minutes will be on Florida. It'll be more global in nature. It'll give you a perspective in terms of why we have a water strategy practice as a firm, its importance to both the public and private sector, and social issues. I'm around for the balance of the day, so despite the fact that we probably won't have time for Q&A, come over and challenge me in terms of some of the slides you see and my perspective. So I thought I'd start broad. I usually use this slide along with a few other slides to frame where we've been and where we're going. This is a projection out to 2025, but basically we have arrived early. This is essentially what the world looks like in terms of water scarcity and water stress. About 3.3 billion people currently live in water scarce and water stressed areas. Roughly about 22% of global GDP is in those areas, and as we look to the future, by 2050, we're estimating about 45%. So this is a current issue. It's projected to get more challenging going forward and impact both the public and the private sector. So when we talk to clients in both the public and private sector, we show the map and ask them to think about where are your operations located, where's your supply chain, where are your customers located, what's your long-term strategy. Again, thinking about how they will be impacted by water scarcity and water stress. Talk a little bit about the nexus. You really can't go to a conference in the world of sustainability of water these days without some discussion of the nexus. It's important that we're having the conversation. I hope we get to the point where we're actually talking about solutions to the energy, water, food nexus. So we need water energy production. There is some discussion of low water footprint, energy production, power production, windmills, solar, and we need energy for water. And then in the ag sector, we need both. So there's no getting around it. These issues don't sit in silos. I bring this up because in part we're going to be talking about data, we're going to be talking about innovation. The two images in the middle, I believe, are part of the solution to this energy, water, food nexus, and how do we provide enough of these resources globally. One is the image of the Internet of Things, big data, information communications technology, incredibly powerful force to address this nexus scarcity issue. And then innovation in partnerships, that's the second image. And we'll get into that in a little bit more detail. So we're on the scarcity trajectory. As was mentioned earlier, we need roughly about 60% more food by 2050, 80% more energy, and about 55% more water, if you believe the population projections. So that's a huge challenge. It's a risk, but it's also this incredible opportunity to rethink how we provide these resources globally. And some of the trends are not changing at all. This is all driven by an increase in population, the rise in the middle class, increased urbanization, need for products that those people want. It's already having an impact. Those images in the little bubble there, that's the Western U.S. We can get into what the impact is on the Florida state economy due to water scarcity. That's China. China is being impacted by water scarcity in both the ag and power generation sector. And that's Brazil. Brazil has a variety of challenges in terms of GDP, but it's been estimated that there's potentially a 1% to 2% impact to their GDP due to water scarcity issues. So it's got a very real public sector impact. The two images on the bottom there, one is from the CDP report that came out, I think about 4 weeks ago, that reports on how businesses are responding to water risk and business opportunities, and the image to the right is the World Economic Forum Global Risk Report that comes out in January every year that ranks the water crisis as #1 in terms of impact. So again, that got the attention of businesses that this is a real issue, it's projected to get worse. It's a global issue. This morning I was having a conversation that we need to stop calling it the drought. If we keep calling it a drought, we believe that hope is a strategy and a good rain is going to make life better. It's really not. This is a long-term trend that we need to deal with, and we need to address it from both the public and private sector. Then all the sectors are impacted to varying degrees. So in terms of risk to your sector, it might be unique, but rest assured it's impacting every industry sector, because without water, we're not making beer, we're not making semiconductor chips and things like that. So I'll talk about the public sector first. What have we learned? The past is not a guide to the future. So the world has fundamentally changed. There is this new normal. Scarcity impacts economic and business growth. So again, there are unfortunately a number of data points to support this view. Public policy will align with the new normal. It's happening. And there are a number of examples of what's happening at the state level. Scarcity does drive innovation. This is sort of the good part of the story, that if you don't have something, you either figure out how to do whatever with less or without. So there are tremendous business opportunities and public sector opportunities there. Innovation and partnerships, business ecosystem, essentially what we have here, are diverse stakeholders that care about a particular topic and are aligned on a solution set, and of course technology solutions. And of course, to bring it into the theme today, data analytics are essential for a fact-based dialogue with stakeholders. So I'll get into that in a little bit, but can't emphasize that enough. Public policy is changing. So we're seeing that in places like California and Texas. I'm from Denver. We just released our final state water plan, thinking about the strategic value of water, the economic value of water to the state economy, and how to address that differently. And then the state of Michigan, they have a draft state water plan out also. Again, thinking about the strategic value of water and how water is an asset and supports a state brand. Though Michigan is positioning itself as a water-rich state and has a unique competitive advantage to attract businesses and drive business growth and economic growth. Private sector, I talked about this briefly. World Economic Forum report, the new one will be out in January next year. I encourage you to look at that. The CDP report, this is a voluntary reporting program, asks companies, global companies, report on water risk and business opportunities. This year they banded companies, they ranked companies based on performance. Again, provides some good insight in terms of how companies are addressing water-related risk issues. How the private sector views water risk. You'll see that this is essentially a term of art. This is how companies think about current water risk and projected water risk. So they look at physical risk. Do I have enough water when I need it, where I need it, of the right quality, and project it out over some period of time? If the answer is no, they have a problem, and they need to develop a strategy to mitigate that risk. Regulatory risk, what are the regulations right now? What are they projected to be over some period of time? In many ways, that's sort of a classic enterprise and risk exercise, thinking about what are the regulations and costs to comply. And reputational risk. So you could be in compliance, you could have all the water you need, but if someone with a social media account disagrees with that, they have the ability to withdraw your social license to operate. So reputation and brand are incredibly powerful in this narrative around water risk issues, water scarcity, and water quality. And then companies think about this across their supply chain, their operations, and even product use. So if you're making washing machines, soap, or shampoo, you care about whether there's enough water in the markets in which you operate. And companies are actually addressing that issue through technology innovation and also engaging with consumers, customers, and other stakeholders. You can then wrap this all together and come up with business value at risk, a dollar value, current and projected, that would impact your business, and start thinking about water differently beyond price. So what companies do, this is a very simple way to look at a water stewardship strategy. It's got basically three major moving parts. It's about conservation, so driving efficiency and water use. Engagement with stakeholders. Water is a shared risk and shared business opportunity and public sector opportunity, so no one player can solve water scarcity issues. It really requires a broad group. And then innovation, technology innovation. And then there are some companies that sit in the middle and do a very good job in terms of getting all these three moving parts put together. This is a very simplified way of looking at a water stewardship strategy. There are a number of frameworks out in the marketplace that align pretty well with this. Growth, not all companies are created equal. There are companies that sit to the left. They basically have no strategy. It's sort of, let me worry. I turn on the tap. I've got water, life is good. I don't know what you're talking about. There's an efficiency strategy. Companies think that they can manage their water risk by driving increased efficiency of use. That'll get you only so far. There's a risk strategy. Companies looking at social license to operate, potentially being withdrawn, and thinking about it solely as a risk issue. There are companies that sit to the far right, which is a license to grow strategy. Thinking about what is their business growth plan globally, in particular in emerging markets where you saw all the red on that map, and how do they develop a water strategy that can fuel that growth, can support that business growth. A couple of things that they do really well, the companies that sit to the right, they understand and quantify the value of water. They develop collective action or aligned action partnerships. So they recognize that they can't deal with this issue on their own, and they bring in a variety of stakeholders to help them do that, including NGOs. They work with competitors in a pre-competitive space. They work across industry segments. So here we get to the data part. Informed decisions based upon transparent data sets. There are a number of examples that I'll touch on. Statewide economic value of water, I'll show you an example there. Reputational risk. So as I mentioned, reputational risk is challenging for companies to quantify, but terribly important. Water infrastructure, customer analytics, and then business value risk and supply chain analytics. Stan, you're going to tell me when I'm almost out of time, right?
You're doing good.
Okay, good, 'cause I can go to lunch. So reputational risk, I can't emphasize how important this is for businesses. And this is an example of a company where we mined social media just as a way to understand what people were saying about this company as it relates to water. And this company had a negative 41.2% sentiment analysis, which basically means people were saying unpleasant things more than they were saying positive things. So if you want to get a sense for potential reputational risk or current reputational risk, mine social media. A lot of chat, and companies do that. Supply chain risk, thinking and sustainability. This is somewhat of a complex graphic here. I bring it up because if you speak to people that manage supply chain issues, they will include environmental and social responsibility or sustainability as one of the sort of macro factors that they pay attention to, but it's pretty low on the list in terms of really quantifying the risk and thinking about how to manage that. That's changing, and this is a screenshot of a beer company that looked at barley production and water-related risk. And you can start to think about, well, what is the current impact or projected impact on barley production, because that's terribly important if you like beer and make beer. And they use this as a basis for investing time and money in their supply chain in terms of transferring best practices and technology adoption and so on. So it's a different way of looking at water risk in supply chain, making very different decisions in terms of how a beverage company engages with their agricultural supply chain. So the companies that are addressing water-related risk do a lot of this. They map water scarcity issues, they map quality, and then use that as a basis for change. Not just driving efficiency in their supply chain, but ensuring that they have a supply chain. Public sector water management dashboard. This is some work we did for the Florida Department of Agriculture, and I'll get into a little bit more detail. This is a screenshot of a visualization tool that we built based on publicly available data. It sort of addresses one of the key questions this morning. What do we need in the way of data? How do we make decisions based on the available data? What new data do we need? So the piece of work that we did for the Department of Ag, we basically helped them view statewide water data differently. And it was a matter of taking publicly available information. We didn't go out and collect any new data. We used everything that we could find in terms of databases. And then we developed an integrated database. So took all the Excel databases, text files, PDFs, whatever it may be, put together a common database, and then use that to create visualizations. Basically, what-if scenarios. So if we're assuming that the state population is going to increase by 5%, but we might be wrong, maybe it's 20%, what might the world look like? This is, again, a different way of looking at available information and thinking through scenarios. And this is based on some work that we've done for the International Finance Corporation 2030 Water Resources Group in places like India. So you can take best practices globally, bring them home and use them locally, and again, give you some very different insights. And these are some of the dashboard examples. This is an interactive tool, so I can change all the variables with a set of sliders. This is obviously incredibly static, but we look at supply and demand, current and projected on the left. We looked at scenarios, again, what if we change crop type, what if population changes, what if cattle production requires more water, whatever it may be. And it goes back to that issue of transparent, readily accessible data that you can start to think about what would happen if some of your assumptions change and what the scenarios look like. Agricultural tactic prioritization, so what if we invest in drip irrigation? Might that improve our gap between projected supply and demand? And then how do you prioritize that? Based on a set of criteria, whether we think this best practice might actually be adopted, even if it's well-funded, things like that. Or what happens if I can't fund this happen? So again, a pretty simple, handy tool to take the data that you have and just look at it differently and think about it differently. You can also do it based on publicly available information that is out in the marketplace. So if you're a company and you're thinking about relocating to California, one of the things you'll want to know is, well, what does worst scarcity look like? And how do I bake that into my site selection criteria? How do I look at it differently? How do I think about it differently? And this is something we just put together for the state of California. Not for the state of California, but using their data. Again, a different way of looking at publicly available water data. Water analytics, predictive asset maintenance, the water utility sector is moving towards embracing data analytics, using it for a variety of different reasons, looking at CapEx, OpEx costs in a different way, looking at operations issues, and then efficiency. So basically, adding additional rigor to decision making with respect to capital investments, how to predict system failure, how to reduce downtime, leakage, and so on. Just a few screenshots here. This is automated notification, so what happens when you get some part of the system that fails. And then thinking about budgeting. Again, the better use of data, making decisions regarding investment and repairs. Solution provider market forecast. I put this slide up because it supports my thesis here about data and being a good consultant. That's always important to do, support your thesis. So this information is a little bit over a year old, but I still believe it's true. And it looks at technology adoption. So what's the market opportunity, for example, in desal is projected to grow almost 9% from 2013 to 2018. Smart meters, almost 15% growth rate to 2019. I found the startup discussion here a little bit interesting, or very interesting actually. 25% of the startups, when this report came out, are focused on monitoring, forecasting, and control. So getting back to the data piece, there's a huge play with respect to data acquisition, analytics, and visualization tools that have applications in both the public and private sector. So I think it's a pretty good data point. This is my most important slide, so please take your time and read this. Okay, want to leave it up though? So Stan, that's my last slide. Yeah. So we're good. How do I do on time?
You're ready. We got 5 minutes for some discussion.
Oh, then I'll keep talking, so there's no Q&A.
Okay. Ernie.
The Department of Agriculture work, is that available yet, or is it still in production?
So I don't know if it's available on their website. Tom may know. We've completed 2 projects for the Department of Ag, so it's public information. But I don't know that the tool that we built is publicly available. So Tom, do you know?
I believe that the visualizations of the results of the data are available. So you can download a viewer, let's say, of that tool, Tableau is the dashboard tool that was used, and they could send you excerpts of the data and you could view it. Couldn't change or modify it, but you could use the tool as they use it. But the work is done.
I just think that's fascinating. I had no idea until last night that it had been done.
I'm biased. I mean, it was a really powerful project with Department of Ag because the feedback we consistently got and they got was, well, we've never looked at the data that way. And that's really one of the things that we need to do. We need to look at data outside of silos. We need to look at it from different perspectives. We need to challenge our assumptions. And with the visualization tool, you can do all that, and you can make it readily accessible to really the layman who just really wants to get a beat on what's going on at the state level and where things headed potentially. Again, it's more scenario planning than anything else.
Great.
Thank you for that presentation. We've done a little bit of work on sentiment analysis associated with social media and looking at conflict precursors for conflict. And what we've found now is that because there's so much awareness that social media is being monitored, that China has this 50-cent party with something like 300,000 people every day are just influencing social media. Bots are generating hundreds of thousands of tweets every second without any human interaction whatsoever. And it's become this big propaganda issue. So we've actually found it to be almost a misinformation device. Have you seen any of that influencing in your sort of markets? And also, have you looked at any ways of verification or filtering against them?
So I'm not a social media expert. So if you give me your card, I'll connect you with the person. I mean, I love social media, absolutely hooked, and talk about water all the time. But to answer your question, we have processes in place where we use it for supporting marketing initiatives with companies. And I've pushed to use it in the world of water so companies can get a better understanding of, well, if a senior executive says something in a particular state, what happens? And how do you maybe not influence that, but understand what stakeholders are saying about the topic as a way to inform your strategy going forward. So, I can't say that I've seen that tweaking adjustment to social media for what I do, but I'm quite sure the person I'll connect you with has.
I really like your information on the Florida Department of Agriculture. We just finished a meta-analysis on looking at nutrient enrichment from various best management practices. I found it fascinating. We found that the micro drip irrigation, is incredibly important for saving water. We also found that it was incredibly important for preventing the enrichment of groundwater and surface water adjacent to agricultural fields. So you have actually a double benefit. If there's a TMDL or BMAP in that basin, by going to the micro irrigation, you're saving water, and you're also preventing eutrophication of those waters, which is a pretty interesting and important connection between those.
That's great. So I'll definitely follow up with you, and maybe we do webinars, and I can show you the tools so we can brainstorm a little bit on that. That's terrific.
Have you got any data or some supporting evidence or something like that stakeholders to discuss water as a shared resource, especially when it comes to Florida, for example, we have a different water management district, they kind of control the groundwater, which is not shared by which are limited by the water management boundaries. The question is, if you're talking water as a shared resource between the stakeholders, or what type of data or information we can present and convince the stakeholders about that?
Yes, so I can send you white papers and examples of collective action, aligned action, platforms and programs that actually work. And what I mean by work is they get a group of diverse stakeholders to row together and achieve whatever objectives that group decides is important. So, yeah, I mean, that's part of the problem we have in the world of water, right? You know, I'm a groundwater guy, a surface water guy, you know, I'm in this water management district, I don't talk to whoever, or, you know, whatever it may be. So how do you break down the silos and share information, present data that we can all make decisions based upon? You know, I think the whole collective action part of innovation is incredibly powerful. But I will send you something on that.
In October, I was invited to be on a panel that was sponsored by the U.S. Chamber of Commerce, working on a real-life scenario in water risk for a company that produces caramel-colored red cans. That's saying, I won't say who it was, but you can guess. And in the water risk, there are several tools that have come out, quite a few of them, but one of the really major ones is done by World Resources Institute, WRI, and in their tool, in their water risk analysis tool, they took population densities and crossed it over with how much available water was there, not just the water availability, but how it's used by the public. And they came up with a world map, and you can zoom in on the tool and find, and you would be amazed at what parts of the world that you think have tons of water that are at huge risk from water scarcity, of not only clean water, but water of any sort. And so the case that we actually did a panel discussion on and make recommendations to incorporation and participation in was a bottling plant in India that was located on the Ganges River. They were going to put it there, build it new, and what we don't ever think about in how this ties together from many disciplines is the idea that there was a religion in the city in India that said the water was sacred and you can't use it to make offerings. And so they were going to rebel and have some real problems with this group. And so the question was, what do you do so the social aspect of this can come into play that we don't really use?
You bring up a really important point. We tend to think of scarcity in terms of physical availability of water. So you can actually have scarcity and stress in places that have a monsoon season, that have 50 plus inches of rain a year, and there's scarcity driven by other issues. So Singapore is a really good example of a water scarce, water stress environment. They get a lot of rain on an annual basis. So scarcity is driven by all sorts of factors. So follow up if you have any questions. Happy to send whatever info you might want. So thank you.
Thanks very much.
All right, so I get the pleasure of introducing the next speaker. My name is Tom Fraser. I'm the director of the School of Natural Resources and Environment at the University of Florida. And I'm also the acting director of the U.S. Water Institute. So all these guys are getting things squared away. In the interest of time, I'll start the introduction. And it's really a pleasure to introduce Dr. Hank Loescher today. Hank is by training an ecosystem scientist, and he's certainly well versed in the myriad issues surrounding not only big data, all right, but big science. At present, he's the director of strategic projects and program developer for international development at NEON, which is the National Ecological Observatory Network. For those of you who may not be familiar with NEON, I think I'd start by saying that NEON represents a significant investment by the National Science Foundation in infrastructure and technologies for the collection of what I would call eco-environmental data across the United States to assess the impacts of climate change, excuse me, land use, invasive species on natural resources and biodiversity. I'm a little cold today. How about you guys? I'm from Florida. I woke up. Anyways, but NEON, from my perspective, again, it's a big deal. You know, we've invested projections, anyways, of about $500 million for setup costs and an annual operating budget of close to $100 million. It's not trivial. I think NEON is the first observatory network of its kind, and it's designed specifically to detect and enable forecasting of ecological change at continental scales over multiple decades. Thousands of sensors deployed across domain sites from Puerto Rico to Alaska will generate terabytes of data annually. So NEON, as I said before, is big in science, but it's enabled by big data. And there are certainly challenges with NEON. There's challenges in the past, there are current challenges, and there will be more challenges. But there are lessons to be learned. And it's in this light, actually, that we've invited Hank to come talk to us so he can share with us his experiences with the program and provide some insights into NEON as it moves forward, and so that we all might learn some lessons in ourselves moving forward. So that said, Hank, take it away. We got this squared away.
Almost. Thank you very much, Tom. And thank you, everyone, for being here, and thanks for the opportunity to be able to chat with you all about this. As we're trying to gin this up, I'm going to take a perspective that's a little bit probably more conceptual at times, and I talk about large-scale environmental research infrastructure, sort of a different type of beast that's large, and what that actually might mean in informing local decision-making as well. My first meeting about NEON, and to give you a sense of the size and the scope, my first meeting was in 1999 and 2000. It went through several near-death experiences, as with many large-scale research infrastructure. That's a separate talk on near-death experiences of these type of projects. It is highly reviewed by the National Science Board and with oversight from the National Academy of Sciences. Once we have a very, very rigorous review schedule and pass that review in 2009, then we start constructing it. It's a 5-year construction process where we have 1 more year to go. And as facilities and infrastructure become built, they become online and become operational, and part of what we have is already operational. So what I will talk about, let's see if I can figure this out. Is that the pointer? May or may not see. I'm going to talk a little bit about the societal imperative of why we're doing large-scale environmental studies. We'll talk about our grand challenges and how we stepped up this process of building something of this magnitude. We give a very broad sweeps of our NEON overview of our design. Talk a little bit about ecological forecasting, why we're doing this, and what are the concepts or the philosophy behind ecological forecasting that we think are novel, and then move into large big data, interoperability, and some international efforts. And then I'm going to lead off with some issues, challenges, and path forward as more of discussion points for Q&A and for kicking off additional discussions here at this meeting. So we probably are very well aware that this is the era of big data. That's what this conference is about. And I have several covers here, and I know Will had put up some similar studies in his first slides. The take-home message here is that it's really becoming very well known across society, not just within governmental circles or agency circles, but also at society as a whole, are recognizing that this is an era of big data.
And we're seeing planning documents and position papers developed from the executive office, as well as in Europe, and Australia, and elsewhere. And this is becoming more and more a societal imperative, an overall awareness, and thinking about the exact problems that we have here today in this room. How do we think about integrating and starting to build these large-scale data sets? One of the concepts that generates a lot of discussion and a lot of effort are something that's called societal benefit areas. You'll see this in planning documents within the White House, again, internationally. And 9 societal benefit areas have been decided. I'm not too sure quite how they all suss out, nor do I really quite understand what the difference between weather and climate is. But how do we actually then think about building large-scale data within each of these societal benefit areas? What does that mean? And the concept of essential variables comes to play. So what are the essential variables that start linking large-scale data within each one of these? So there's essential carbon variables in here. There's essential biodiversity variables in here. This is a grand challenge for environmental sciences as determined by the National Academy. The White House actually placed a large big data initiative to start generating what this discussion would look like across SBAs, how to at least conceptually link large platforms. And it's also started the discourse that big data is a national resource, and being able to communicate up through our governmental and decision making that this is really, really important national resource. The second part is that once we actually build, the vision is that once we actually build these type of large scale platforms, we're then able to ask not only questions within these societal benefit areas, but across them in ways that we haven't even thought of yet. So really being able to look at in very much towards the future of new questions that we don't even know what to ask yet, but being able to develop the facilities and the data structure to be able to ask them. So the questions of societal importance within and among these societal benefit areas, and that understanding really requires that integration of information. And lastly, and I'm going to circle back around and not spend a little bit of time on this, but in my lessons learned internationally, that to think about how to do this, it's really a change of culture. It's having people-to-people contact and meetings like this that were actually evolving and having this discourse and changing that culture. And that is, for me, much of the change and how that change actually occurs. These are some quotes from our executive branch. If you're not familiar, I strongly suggest pulling up the National Plan for Earth Observations that came out last year. It's well recognized at a very high level that fragmented federal investment on monitoring ecological change weakens our national priorities. That there's a bond and a strong link between economic and environmental dimensions to societal well-being. And while there's plans within agencies and among agencies to start thinking about this, look around the room right now of the people next to you, because this is actually where the real work is being done. It's as we are actually building these networks, building these new cultures, and pushing this forward. Okay, so I'm going to talk a little bit about NEON, and hopefully the narrative will build as we go on. Part of that then is with the National Academy of Sciences through NRC reports in the early 2000s, had 2 very seminal reports. One are the grand challenges of environmental sciences, and the second is sort of a vision of what the National Ecological Observatory Network could be. And they actually identified 7 grand challenge areas. And you see them here: biodiversity, hydrochemistry, climate change, ecohydrology, infectious disease, invasive species. And so we took that to heart. We went to the community, and it was a community-driven process. But what does that mean? What are the questions that you actually need to be able to address these type of large-scale grand challenge questions? And so from the community, this is our mission statement. This is what NEON does. How will ecosystems in the United States and their components respond to changes in natural and human-induced forcings, such as climate, land use, and invasive species, across a range of time and space scales? What's the pacing pattern of those processes? And how do the internal responses and feedbacks of biogeochemistry, biodiversity, ecohydrology, biotic structure and function interact with these changes of land use, climate, etc.? And what's that ecological context? Now, we probably will never ever be able to answer these questions, but these are meant to be high-level guidance questions of how to build a design in a facility. And what you'll see there is that we've adopted the cause and effect paradigm explicitly. What are the forcings? What are those abiotic drivers of change? What are those responses? What are the organismal responses with the changes in biogeochemistry? And what are the interactions and their feedback? And being able to adopt the cause and effect paradigm, as well as the spatial scaling strategy across the continent, has been deemed by the National Academy as being truly novel. I wanted to talk just very quickly about what we mean about ecosystems and ecosystem states, and how they potentially will change. So this is a conceptual diagram of the stability of an ecosystem as a ball on a plane. And you can see that, and here you can actually, the ball might move very, very easily if there's a perturbation. Very small perturbation would change the position of this ball here, as well as this might be one that would be considered very stable. So these are concepts that we use and much more in a conceptual way of being able to describe resiliency, adaptability, and transformability. Resiliency is the propensity of these balls or these ecosystem states to move from one state to another. Adaptability is their ability to resist or to adapt to particular circumstances while still maintaining that state. And transformability is actually moving energetically, or that whole ecosystem structure and function, to a new state. And these are some of the concepts that we use. But we also do that under the idea that of classic disturbance ecology, where a disturbance such as storm events, hurricanes, snow and ice, large-scale fire, etc., insect outbreaks, affect the biotic structure, the organismal structure, which in turn affects the resources, and there's a feedback loop. And that's a discrete disturbance. But as we also all know, that we also have chronic disturbance. We've got increases of nitrogen inputs, temperature affects the sea level rise, increases of population in CO2. So there's chronic resource altercation. That actually affects the resources themselves, which then in turn affects the biotic components. This is a very different paradigm of what we potentially can expect in the future, because all of our understanding and our theories are all based on discrete disturbance. And we have no new ways being to address continual chronic alteration. And so these types of theories and concepts really can only be challenged across time and space scales with large-scale integrated data sets. The other novel aspect of how we actually design NEON, and this might be really intuitive to many, is that we've actually come up with our grand challenge questions, which you've seen. We went to the community and thousands of people that we've asked, how would you address that question with your own specific hypothesis? And so we have lots of different environmental science questions. And then we ask ourselves, well, what are the data that you actually need to be able to answer those hypotheses to address those grand challenges? And then that says, well, then what type of requirements that we need to actually build to? What's the signal to noise? What's the accuracy that we would need for particularly type of sensing or type of organismal sampling? What's the spatial size that we need to have a certain signal to noise to be able to answer that question? Those are science questions, science requirements, and then how do we actually implement that technically flow to technical and design requirements? Now, this might seem really intuitive, that requirements flow from the top down, and at some point we collect data, and that data then flows back up to be able to address the grand challenge questions. This process, this design process, is very common for things like NASA satellites or for particle accelerators. This is entirely new and different for the environmental sciences community. No one has ever done it at this scale, and no one's ever moved from a hypothesis-based questioning or a hypothesis-based structure to a requirements-based structure. And it's not to say that we don't have questions, we clearly have questions, but we're putting it into a different context. We were forced to do that by the National Science Foundation, because with that, we can actually now constrain our budgets, our schedule, our risk to actually build something like this. But now that it's imminent, that it's being built and we're somewhat operational, this is the structure that we can actually say, these are the actual sensing and the actual signal to noise that we actually have, and how to interface that with other types of organizations, whether that's your own study, if you want to be able to add things to it, if you want to integrate it to other different data platforms, if you want to be able to integrate it in different types of field platforms. So it gives us an incredibly robust tool. My work internationally, now that there's other continental scale observing networks that are coming online, a lot in Europe, Australia, China, etc. This is the means by which we communicate. What are your requirements and how do we actually link that up? So this becomes an incredibly powerful tool. We also went to the community and said, if you were to assess the regional trends for a wildland site, for ecology in your area, where would that be? And also, what are the questions that are most relevant according to those grand challenges that are in your area? So we went to also to the Department of Energy, and we carved up the U.S. into 20 ecoclimatic zones. And within each of those zones, we have a core wildland site that is depicted by these black dots, and that they're there for 30 years. The one here is actually right outside of Gainesville in Melrose at the Northway Swisher. And then so we have two other sites per domain. We're very jargon rich, so I'm trying very careful not to speak in different acronyms and jargon. But within each domain, we have two other sites. And again, we asked the community what would be the most relevant ecological question for that domain. And here in the southeast, it was forest management, around forest management and restoration issues. How do we restore different ecosystems? So the other site is at the Jones Center, if anyone knows that, and Disney Wilderness Preserve. Another example in, say, in the Pacific Southwest, that came back as saying that we really don't know the effect of the snow-rain transition and how that's changing with land use change and changing the boundary layer dynamics, that in turn is affecting snowpack and the water resources that are in the Sierras. We have an altitudinal gradient to be able to assess that. So across the continent, we have other ecological domain, gradients that are embodied across it. And some of those include agricultural themes, climate themes, ecohydraulic, forest systems, invasive biology, etc. Across our sites also, we have, so that's a total of 97 sites. And at 36 of those, we have explicit aquatic sites that we also measure. And they tend to be first order and low order systems that also then map to different types of hydro periods across the continent. And I would say we're acronym rich. So at these sites, we have different science teams or science areas that we actually then sense what we're doing. We have suites of organismal ecology, and that's primarily human observations in our bioarchive. We have suites of automated instrumentation. We have an aquatic system that is a combination of both human observations and instrumentation. And then to take that, that information that's local and being able to scale it at the area that we can actually link to other explicitly spatial data sets, possibly from the US government, like satellite-borne data, BODIS data, aqua data, etc. We have an airborne observation platform. And we integrate that at higher and higher levels with our data products and different types of other analytical packages that we call our land use analysis package. So a little bit more specifically, our fundamental sentinel unit, or FSU, our human-based observations. We have whole suites of data products on biodiversity, population dynamics, productivity, ecohydrology, biogeochemistry. Our data product lists are large, so if you're interested, I'd be happy to point you in the right direction, but you can find them and you can actually access our data on our web portals. We have data product catalogs that then also describe all the types of data that we're collecting. So here I'm just giving a broad overview. Our fundamental instrument unit is tower-based. Again, co-located with all of our organismal sampling. We have measurements on physical and chemical climate forcings that include things like NO, NOY, full range of oxygen isotopes in water, so we can look at source and sink dynamics. Lots of meteorological scalars and fluxes, so in other words, we look at how whole ecosystems breathe in real time using sound waves and lasers. And we can see how much CO2 is being uptaken and water being emitted in real time using ecovariance, if anyone's familiar with that. And to give you an idea also then of the amount of data that's generated at one of these sites, it's about 50 terabytes per year, and we have almost 100 of these sites. So it gives you a scope of just this type of instrumentation of how much data that generates. The towers tend to be very iconic. Everyone says, oh, look, you've got a tower site. And that's what it is. I also want to say that, in our statement, our mission statement, our grand challenge statement, that we want to look at the pace and pattern across scales. And towers, even though they're in a single place, we're actually measuring many different types of scales. We're measuring the synoptic incidence scale. We're measuring the microclimate scale, the amount of scale that the vegetation and the structures actually modifying the local climate, and the flux scale. It's a moving plume that we actually measure across the ecosystem that can go out several kilometers. And of course, then also the soil scales. Our aquatic reaches, again, are low and first order streams and ponds, and they're designed to look at the connectivity with the terrestrial environment. In the stream reaches, we have an observational stream reach, and we also have an experimental stream reach. Measurements like metabolism, reaeration distances, all the abiotic drivers, light, temperature, and so forth. This is actually here at Barco Lake at Ordway Swisher. It's one of our first platforms that we've actually put out in lakes. And this is not just a prototype, but this is up and running, and data is being collected right now. Our airborne system, we have got 3 aircraft. We are flying all of our sites right now at times of peak productivity. So whenever that occurs in the summer. And it consists primarily of two instruments. One is a high-resolution imaging spectrometer that returns the irradiances from the ecosystem, and a downward-facing waveform LiDAR. Linking these two sets together, and this is modeled after the Carnegie observation platform at Stanford. What that does is the imaging spectroscopy returns different irradiances, and those can actually be turned into things like foliar nitrogen content, foliar water content, other metrics of productivity and water use. And you combine that then with the canopy mapping, the structural mapping, and our DEM, and you can then build out actual real maps of whole ecosystems and whole forests as a function, in this case, of foliar nitrogen. You can see that there's a much higher foliar nitrogen in this ecotone area between these. This happens to be Ordway Swisher. This is local data. This is real local data. Pine woods in the back, flooded prairies in here, and then the ecotone hardwood hammocks you see is going to in terms of foliar nitrogen. Okay, so we are charged to enable an understanding and forecasting by providing all of these data. We are data producers, and we're looking for user communities at that forefront. We do this by supplying informational infrastructure, consistent, long-term, continental, multi-scale data sets for research and education, and the physical infrastructure, that research platform for investigator-initiated sensors. So we also have the capability of adding other sensors. Like I said, also, we have things like 3 aircrafts. We only need 2. You can request that 3rd aircraft to fly over your sites to expand and to connect to the large-scale data sets that we're generating. And so if we want to talk a little bit more offline, I'd be happy to discuss that. But I would also be remiss in there it is, sorry. In that we also have lots of other structures. We have a very active education and outreach group. We have a state-of-the-art calibration lab that's very important for interoperability, which I'll mention in the future, etc. So there's a lot of things that can be requested that we should talk about. So we provide that infrastructure. So if we are to provide an infrastructure to enable an ecological forecasting, we had to actually define what we actually meant by ecological forecasting. And so bear with me for a second. I don't know if anyone has ever seen this before. But this is real data. This is the NOAA forecast scale of how well they can actually predict the pressure fields across the whole continent at 500 millibar. That actually dictates the synoptic scale weather patterns across the US. And in 1955, their skill level was around 22%. And now in 2015, it's a little bit over 80%. And so this is the forecast at 36 hours, and this is the forecast at 72 hours. Now, what's really interesting here is that there's no huge stochastic jump here when 3,000 new weather stations came out in the 60s. There's no huge stochastic jump here in the 70s when weather satellites came on board. And there's no stochastic jump here in the 2000s when supercomputing came on board. The way that they actually integrated and increased this forecast scale by integrating theory with their models, with predictive forecasts, challenging those forecasts with observations in an iterative capacity. Now, that might seem very logical to us today, but if you're talking to other research groups or other agencies, they say, oh, we just do experiments, or oh, we just do observations, without necessarily the goal of ecological forecasting. But the robustness of this model of being able to iterate theory, model, forecasts for ecological science is actually fairly new. We all say that we might do it or think about it, but actually explicitly saying that this is the concept of how we're moving forward in ecological forecasting to enhance our skill, this is fairly novel. The part that's missing, and no one doesn't necessarily need this, is the role of experiments. And clearly, what we're experiencing in environmental sciences right now, particularly in light of chronic disturbance, like I mentioned earlier, are nonlinear stochastic processes, things like tipping points, temperature sensitivity, susceptibility to drought, etc. So we need to be able to use experiments to elucidate these future conditions and integrate it into the observations and theory and forecasts. So that calls for giving estimates of system state, information on process level parameters. We need to have those experiments to elucidate those unknown and nonlinear processes. And we also need to have those observations then collected systematically over time and space to challenge these forecasts. This is novel novel paradigm for ecosystem and ecological research. Now, I've been giving these two slides in one form or another for a number of years. I also realize that while this is what NEON does, and this is really novel, and it is really important to push it forward, it's not necessarily what's needed when we're thinking about analytics and applied components. That would also, what we need to be thinking about around ecological forecasting is being able to better communicate as scientists, as academicians, in engaging in this process, the concepts of risk and uncertainty. And also, along with that, is to be able to determine and be able to communicate not our science in terms of absolutes, but in terms of decision-making spaces. And that is also very, very foreign for us to try to think about. And maybe there's some more questions around how we might think about doing that. But again, this is sort of this is a frontier talk, right? That's why we're here, we're chatting. Now, here's Earth observation networks. So we're very big in infrastructure. We've got very little on-site experience and marginal site-specific understanding. And there's very few of us, right? There's the integrated carbon observing system in Europe. There is the terrestrial ecosystem research in Australia. And so they're really important that they're very strong, large data sets, large amount of data. We're now starting to think about how do we actually ask questions that span whole continents. And I can give examples of those if you would like. But we also are in the federated world, lots of other types of environmental and aquatic and ecological research. Coordinated distributed experiments, long-term research networks, and large amounts of PI-driven research, all with their different levels of on-site experience, infrastructure, and site-specific understanding. And so the question then becomes, again, this is from an infrastructure standpoint, but how do we start thinking about integrating all of these together? Both in terms of physical infrastructure and the informational infrastructure. So that comes up with the concept of interoperability. Again, if you read many of those planning documents that I showed in my very first slide, they all say, oh, we need to be interoperable. Well, what does that really mean? And how do you have that conversation? So the interoperability fabric is what's between all of these large-scale observation systems, and what are the analytics and the applications that we want to be thinking about of actually generating. So how do we actually make these disparate data sets interoperable? How do we actually make interoperable data then into applications? And it's really up for us to figure that out. So we've defined interoperability in terms of scientific utility. Now we might think about it in a very different way if we're thinking about outreach components or with our educational goal. But for us, the way that we're delivering data, we really want to be able to identify what do we mean by interoperable, so that we can actually put real boots on the ground activities to be able to make different platforms and different research activities interoperable. First is how do we actually align our science questions, our hypotheses, our requirements, our mission statements. This actually defines the joint scope of how we actually can work together. What we have to offer, what you have to offer, and where those gaps are, where we actually need to think about putting additional resources to do that. So we can ask then, what must be done to ask a particular question or for a particular focus or to join a particular research infrastructure. The second is traceability of measurements. So again, that's the epistemological question. How do we know what we know? So the use of standards, recognized standards, first principles, best community practices, know and manage towards the signal to noise that you're after for whatever phenomenon and process that you're after. And uncertainty budgets, and I'll get back to that in a second. The other is algorithmic processes and procedures. It's fine if I have a data product of, say, metabolism length scale for first order streams, and you have a different algorithm to do that. That's fine. But to make it consistent and compatible, we actually have to then intercompare them and to understand what their relative uncertainties are. The reason why I'm bringing this up is because the future and the state of the art of integrated models is through Bayesian approaches or data assimilated approaches, where we need to know what the uncertainties are a priori, and then we can actually model that up front. So whether you're looking at the NOAA forecast skill that I showed up before, or other predictive ecological models, the state-of-the-art are Bayesian approaches, and we need to know what those uncertainty buckets are a priori. The fourth component is informatics. Now, many of you probably work in different levels of informatics. I lump a lot of things into informatics. I run several large projects around informatics. I put a couple here, but I've actually spelled them out in a different way. So one, specifically what we mean are data in metadata formats. Make sure that they're transferable and standardized. We use the ISO 19115 compliances. Persistent identifiers. Everybody knows DOIs, digital object identifiers. But when we're thinking about time series data, how do you then have, as part of our scientific premise of reproducibility, how do you pull a specific data set and be able to identify exactly that length of data set if it's part of a time series? And also, how do you then change that persistent identifier if that time series is constantly being augmented? Data policies, open source, community acceptance are what we're moving towards more and more. And there are hybrids for different business models. Data management plans, all of the US agencies are now mandated to have data management plans. They're not aligned in any way, shape, or form. Data sovereignty for moving across geopolitical boundaries, intellectual property rights, and discovery tools. And I've left ontology, semantics, and control vocabularies, because this is actually one of the places, at least in biodiversity and environmental sciences, that UF is actually considered a leader, and is actually pushing that frontier very strongly. And I'm going to give you an example of something that I personally have come up with. So one of the measures of ecosystem productivity is litter flow, how much litter is produced, how you collect that. But there's no real way of quantifying or categorizing or putting that into a controlled vocabulary of what litter flow is from one site to another, or from one research to another. There's no standardization, there's no best community practices to do that. And that's sort of a simple thing to sort of wrap your head around. The more complex thing is the idea that NEON is actually measuring the presence and absence of infectious disease, specifically for this particular data product, vector-borne diseases of mosquitoes. And so how we actually do that is we collect lots of mosquitoes at all of our sites, we grind them up, and we do DNA analysis. And we then look at the presence and absence of hantavirus, of West Nile virus, and dengue. There's no word for that crushed up chunk of sample of mosquitoes. What do you call it? How do you put that into a searchable ontology? There's no way of actually doing that. The place where these components of interoperability and informatics is being played out in the worlds that I work in are other large-scale forums, international forums, and across other large-scale research infrastructures. So I work with space weather, geodesy, seismology, biodiversity, coastal sciences, carbon, etc. And the places where we have these discussions are other forums. Research Data Alliance, GEO, if anyone knows GEO, Group on Earth Observations, the Belmont Forum, ESIP, which is the Earth Science Information Partners. And I encourage a dialogue here of how do we actually bring them into this discussion and into this group and vice versa. I think this is very powerful and untapped resources of how we're actually thinking about working together and integrating our cultures together as well as the informatics that we bring to bear. I'm going to talk about two models that I see with research infrastructures. One is the web crawling or the web brokering activities. This is really busy. And it basically says that there's a system, a broker that's able to know where your data is and pull it in and federate it in a different way. That then requires a registry program. So if you have your data and your informatics and your metadata platforms and your data management plans, etc., you place those into a registry and what your standards are, and it automatically brings it all together according to the semantics and ontologies that you've identified for your data set. The early stages of this, at least on the group on Earth Observation Systems of Systems, was kind of clunky. It's gone through several different iterations. It's supported by the UN as well as lots of different governments have treated onto it. And so this is one tool that is continuing to grow, and there's different flagship and different disciplines, water being one of them, of how to bring together and federate large-scale data sets. The other, and this is the AMP lab, this is a medical example, and that is actually coming up with a system architecture ahead of time and understanding and being able to say what each one of these different analytical packages are, and then partnering public and private to be able to realize that. So coming up with a system architecture ahead of time, and then modularly being able to assess the analytics and describing their interrelations and the interoperability, or the interrelations and the interfaces between these analytics in a larger cyber infrastructure space. This has proved to be an incredibly strong model. It's gleaned several hundreds of millions of dollars to set this up as a prototype with large public and private enterprises, including Google, Microsoft Research, etc. So this model has actually gained a lot of traction and a lot of optics. And I think this is a very strong model to think about for environmental sciences. And I'm starting to see these building block approaches starting to emerge. Okay, so some take-home messages, things that I haven't talked about. Environmental data and aquatic data is extremely heterogeneous, from images to spatial and time scales to different types of signal to noise generated across a variety of different platforms. It's long-tailed. There are lots of smaller data sets that might be incredibly relevant that we don't know how to mine and how to pull in, unless we have things like data registry processes. And multiple use, how do we actually augment and build upon the accessibility of these long-tail data for more and more use. Something I have not talked about, we had recently run a large international conference. It was sponsored by the National Science Foundation to readdress the grand challenge questions. Are they still valid or not? And are there new grand challenge questions that we should start thinking about? And it was 3 days. It was an incredibly active and dynamic workshop. We're having some papers come out of it. And one of the things that was recognized are things like the IPCC report that already has some ecological forecasting. Now, I'm a big proponent of the IPCC report. However, those forecasts that go out 25, 50, 100 years actually also does a really large disservice, and that disenfranchises the public and many decision makers of why do I have to make a decision now if the uncertainty is 100% and it goes out 50 to 100 years. Why should I change my behavior on the coast today? And so one of the challenges that we don't know how to do, short-term ecological forecasts from the year to the 5-year time span, and being able to develop that trade space and that understanding around that. So that might be sea level rise, that might be flow regimes, that might be when is the summer onset of drought year actually going to occur. We don't know how to predict that. We don't know how to predict leaf out in the spring, which has huge bearing on food security, how I make my natural resources decisions. We don't know how to do short-term ecological forecasts. Large-scale environmental data is here, but interoperability, those searchable platforms, those applications and analytics, they're all lagging. That's why we're here. That's why we're having this discussion. I'm stating the obvious. It's good to state the obvious at times. And I'm seeing more and more of the model of the building block. How do we do small, manageable pieces of this larger puzzle? And institutions are becoming much more of that middleware between large-scale environmental data sets and those applications. And this is, I think, new business models, new hybrid business models, public and private, and we see lots of different players. I said at the beginning, I talked there's large expectations for societal benefit. Again, that's what we are charged to do. Integrating our environmental data is truly a frontier science, and we should all recognize that. It's not just our day-to-day grind, but this is a frontier science, and it's a grand challenge. And my work around, I'm really seeing that a big piece of it is how do we change the human capital? How do we change the cultural capital that we bring to bear? How do we actually bring together and evolve the broad adoption and evolution of these cultures to use large-scale data? Still is a challenge, and this takes time, and we should recognize that. But person-to-person, people-to-people contact is extremely important. And something I don't know if we're going to be talking about here at this meeting. How do we train and educate new cohorts of users, and then we all should be taking leadership. And with that, I will hopefully go to the next slide. And thank you for your time, and hopefully I had an interesting discussion. I guess you're moderating.
I'm moderating, so fire away. I mean, there's a lot of interesting questions. And I guess one of the first ones I would have is with regard to the users of this data. I mean, it's publicly available. It's a huge investment by our
Hey, use the microphone.
Okay, sorry. What I was saying is that it's obvious, and I said this at the beginning, it's a huge investment by our federal government. And I want to know how the users of this data are reacting to it. Are they taking advantage of it? What is the feedback? What are the problems that they're experiencing? Will they make changes?
Great question. We fully expect things like data portals, accessibility, how we report data, that's going to evolve. And we have resources budgeted to make sure that that happens. In terms of building this, our ability to reach out and engage the community has always fallen short compared to the amount of time and resources that we need to actually build it. And our guidance from the National Science Foundation is always to look inward and to build it, make sure that we need to build it. With the caveat that we engage the community with workshops, with advisory boards, technical advisory boards, etc. And that has been throughout the design period until about 2 or 3 years ago, where now we're able to engage and have a bit more bandwidth to engage with the community. Large early adopters are, not surprisingly, young graduate students are jumping on this left and right because they actually see that this is as a frontier and part of their career. We are starting to work and have conversations about what it would look like to have a public and private enterprise to use the data. So a synthesis center is gaining a lot of traction. And then since we swim in the sea of large-scale infrastructure, other large-scale infrastructures have that same problem. And so a lot of our discussion of how do we work and engage with user communities are in conjunction with Australia TERN or China CERN or the European components. And there'll be more and more opportunities to engage with us in the coming years. We've got resources and new projects that we're stepping up for broader engagement.
I will let you. No, we don't need to make this complicated. And keep it going. You want to answer.
Yeah, to the back.
I'm a user of data all the time. I work on large projects, and so almost always we'll look at what's available at the broadest field and use that for context. Then we zero in and always collect site-specific data. I'm curious who you see as the primary users for this data and for the
tools that we make available? How do you expect them to use it?
It's large. The primary users are going to be probably twofold. One, this opens up a whole new world of how do we ask continental scale, regional to continental scale questions. How do we scale up in those activities? Agencies are really interested in that questions. Graduate students are really interested in that question. It's called macro system ecology. And how do we actually start thinking about asking questions across continents? Which I'll give you some examples which are very interesting. So we have this one platform, and we're thinking, and half of our users will probably be thinking about how to scale up. The other half, just like yourself, or how do we actually take that contextually and scale down, whether that is in time or in space. Again, I see both of those being very active research areas. One more theoretical and the other much more applied.
I may have missed this. What is the extent of your network? I know it's a national observatory system, but can you elaborate a little bit on the extent of the network in terms of spatial number of stations and also temporally? How long does the data go?
Sure.
10 years?
Yeah, no, so it's with all of our design and research development, it's $500 million to construct. We're almost done constructing it. We have sites from the North Slope of Alaska in Barrow and in Tulip all the way down to Puerto Rico. And we have sites in Hawaii all the way out to New England and everywhere in between. And they're distributed according to what the research community came back and said what was important. Now they're fixed, and I fully acknowledge that there might be really strong and important questions that we can't address with our fixed resources. So we have those themed sites, if they can stay there for the duration of NEON. But if they're not collecting data that's important, the community like yourself can say, well, we want to move it to another site. And we have resources to do that. We also have what's called mobile platforms that you can request. So if there's targets of opportunity, things like a flood event that you want to be able to assess really rapidly, we can come in very quickly and assess that for you regionally, or a forest fire, etc. So spatial extent and the dynamicism of our design is flexible, while we still have fixed sites as well. Our operations is for 30 years, and that starts end of next fiscal year. And so we're guaranteed operational funds as part of the agreement for the construction funds for a 30-year period. And we fully anticipate there'll be upgrades on cyber infrastructure and models and, you know, as things go on, or instruments, et cetera, as things go on. But you've got a follow-up?
Leading question, yeah. Do you leverage an existing monitoring network as you do that? Or do you just build new stations?
Yes and no. So the National Academy and the National Science Foundation, when we're designing this, did not want to have this design contingent on any other agency delivering something to it, right? But we also recognize that we can't swim in that sea without engaging and partnering. So many of the sites overlap with other existing agency projects. So we are at multiple sites that are USDA ARS, Agriculture Research Stations. We have other ones that are at NOAA Climate Reference Network stations. We're at other ones that are at long-term ecological research stations, and at critical zone observatory sites, and so on and so forth. And so, and American DOE Ameriflux sites. And so with that, then we have a mechanistic linkage of having our measurements right at the same place as their measurements, so we can extend the sphere of influence if they're relevant questions using multiple different platforms. Does that make sense?
Can I ask a real quick question? I want to follow up on that. So, I mean,
Sure.
if you do want to, for example, take advantage of an event, all right, and you want to move some instrumentation or who do you make that request to? Do you make it to NEON? Do you make it to the National Science Foundation?
Yeah, it's a really important question. And we've been working with the National Science Foundation for quite a while to come up with the process to do that. It will, and hopefully we're going to unveil that soon. Okay. It's modeled after the use of the Spitzer Space Telescope. And so there's a feasibility component, there's a feasibility review that NEON does. Can we actually do it or not, right? And what that cost would occur. And then for you as a PI, there would be a scientific merit review. And that merit review would be similar to the rapid proposals that would be at NSF. And so then if you get funded and awarded, NSF gives you the money to be able to do the science, and NSF gives us the money to actually implement it and execute it on the sites. So one of the other rationale that I didn't talk about for NEON is that they want scientists and engineers to spend more of their time doing science rather than setting up sites, so developing that infrastructure. So we facilitate you doing your science. I like that.
I wanted to pick up on your compelling point about the interrelationship between data collection and data analytics and the development of taxonomies and especially as we're moving into an environment where we're less and less, let's say, data limited in terms of the next generation of breakthroughs and more analytically limited or creatively limited. I spent 5 years during the MREFC phase as a director of your sister facility, Ersco.
And I work very closely with Ersco.
Okay. We had very strong community support for data collection, data archiving, portals, and distribution. When it came to developing the next generation of creative analytical tools, I don't mean data visualization, I mean real sort of data analysis tools, we could not, for whatever reason, get the community to come together and create a support on that. It was still seen, that's where people wanted to retreat back into their individual labs and their individual offices and their individual groups of graduate students. How is NEON going to break through that? How are you able to get people to get beyond just a data collection and distribution facility and get that community input to develop the analytical tools that are really required to exploit this amount of data?
No, it's a real pertinent question. And very truthfully, that's right where we are right now. We're asking ourselves that same question. We engage in multiple different forums to be able to make that data available, but to bring together the different communities for specific purposes for those applications. We're engaging with synthesis centers, specific research groups that self-organize, so RCNs, and helping support RCNs or the like. Different universities, different initiatives that we are targeting to identify early hanging fruit rather than trying to do a large shotgun approach initially. And hopefully we'll be building momentum around that. But that's our current strategy. We're not fully operational yet. And I think it actually, NEON presents a little bit of a different problem than Earthscope, both IRIS and UNAFCO, because their communities are already extremely well built around how to use research infrastructure, where the environmental and ecological communities, this is the first of its kind, and they still don't even know really what it means and what it means to them for their science. So we have to overcome that burden on top of that.
I had a question about sufficiency of data. You had a slide up that said the data is there, but the way to actually get to it, the interoperability of it isn't there. I'm wondering, how can we actually say that we have enough data collected at this point? Are there any measures of sufficient environmental science data, established so that we can say, okay, we're there, we finally have enough data? Is there any thinking about that? Is there anything within your framework to sort of quantify whether we've collected enough data?
I'm not too sure. I know what the question is. Interoperability is different from being able to produce data and make it available. So we've got data that's available. But the degree by which it becomes interoperable is the degree by which those 4 points that I laid out are actually met, real tasks can be put towards that. So that way, how you would integrate our data with somebody else's or your data with somebody else's. The metrics of the actual data, whether or not you can answer a question or not, what informed our designs, our temporal coverage, is trying to assess what the known signal-to-noise ratio that's known, what we know today, or that we can model today in terms of accuracy and precision. So how much data that you would actually need to be able to be accurate and precise to be able to use the appropriate statistics to answer your question. And so we have metrics to be able to assess what our design is, and now we're collecting the data to test that.
So
Does that make sense?
That makes sense, yeah. So to follow up on that, have you defined a sort of a library of science questions that you are, measuring this data against? Or, how are you anticipating what the science questions are?
Well, so we asked the community for those science questions, and we've generated thousands of them. We had cataloged those for our National Science Board review. I don't know if they're publicly available or not, and one of the reasons is that we didn't want to give any particular research group competitive advantage over another if they came up with that question. And so we used it for our internal discussions and working with the National Science Foundation. But yes, we did generate lots of different questions, but that's somewhat, we lumped them together. So say if it's around productivity, around carbon productivity, we want to know within, say, 20% of the spatial mean for litter faults, if I use that as an example earlier. And depending on how many plots that we actually put out there, it becomes an n-size sampling analysis. And so that's a very easy thing to be able to assess what that signal to noise is and how that would extend to our design.
That would be a fascinating database to see.
Yeah.
The list of questions.
Yeah, as well as what we do make available are all our requirements, which are also pretty incredible. So,
I think
be
it's
patient.
a great program we have. I'm just wondering, you've got USGS, EPA, Fish and Wildlife, NOAA, other organizations that have this huge data collection. I was wondering if they were cooperating with you, because it seems that would be a perfect match or a perfect fit if you could somehow align some of the data they're generating and feed it into your system and make more of these global. For example, like you have those really cool towers where you're collecting atmospheric data. I know EPA is interested in mercury contamination all through this atmospheric deposition. You could take and collaborate with them and have a national mercury TMDL to solve the problem, figure out who needs to do what to reduce mercury over the next 20, 30 years or whatever. And it seems like a perfect fit, and I was wondering if they were cooperating.
Yeah, so I heard two questions. One is cooperating on information, the other is on the physical infrastructure.
Right.
Yes, we've got a big sandbox, a lot of people want to play with us. The problem right now is that we are extremely focused on trying to build it and develop the plans for engagement and to make sure those lines of communication exist now, and they are. So EPA is a perfect example. They want to put methyl bromide sensors on all of our towers, right?
Oh, okay.
So we work very closely. We've got offices in DC and communicate and engage with them on lots of different levels. Now, that is for the physical infrastructure. We're also at a lot of agency property. We don't own any property, so we're at Forest Service land, we're at BLM land, etc. And so they're very anxious to know what that data looks like as well for their own internal purposes. And then lastly, I had mentioned the Eco Forum of the 200 Million White House Initiative. That was specifically designed to address that question. How do you get all of them to talk to each other and make sure that they have a homogenized or harmonized data management plan? Or how do we address those other issues of interoperability? That's, as you can imagine, a harder conversation to have.
Well, you see what's happened to the storage system that EPA has been using for 30 years. I mean, it's a mess. I mean, those things need to be fixed up nationally. Yeah.
I sit on a couple of interagency working groups also. This comes up a lot, and really strong players are USGS, particularly the Aero Center, U.S. Forest Service, NASA in the ROSES program, and DOE in their terrestrial ecology program.
Anyways, I see Stan standing up, which means we're due for a break, correct?
Yeah, Tom?
It's just a quick question. I was just interested, have you seen the growth of like autonomous instrumentation evolve with this as far as like robotics or data collection, without the need for human involvement?
Maybe that's a conversation to take offline a little bit. Data collection, yes. We actually have developed a whole new method of data acquisition that we think is incredibly robust, particularly for large-scale observing. Turning everything to digital right at the point of measurement, even if it's an analog measurement, and then managing